All right, welcome FUTA 100 level students. If you're gearing up for the MTS 102 exam, you are in exactly the right place. Consider this explainer your ultimate tactical briefing. We're going to cut right through the noise, completely decode that massive course manual, and build a solid strategy for you to absolutely crush this paper.
Look, let's just be real for a second. I totally know the feeling. The late-night calculus cramming, the sheer panic when some wild kinematic integration question pops up out of nowhere, or the utter dread of staring blankly at tutorial sheet 7, just wondering where the numbers even went. It's stressful. Your anxiety is completely valid. But today, we are officially changing the narrative from panic to power.
So here is our roadmap to victory. We're going to tackle functions and graphs, limits and continuity, differentiation rules, integration applications, and finally, wrap up with strategic mindset. Let's get moving.
Section 1. Mastering Functions and Graphs. This is basically our first boss battle, covering the foundational building blocks of the entire course.
Okay, so every function has rules, starting with what goes in and what comes out. The domain is your set of valid input values, and the range is your output. Think about that classic analogy from your manual, assigning Nigerian states to their capital cities. The set of states, like Kwara, Akwa Ibom, or Anambra, that is your domain. The specific capital cities they map to, Ilorin, Uyo, Awari, that's your range. It's simply a mapping of one set to another. Really straightforward.
Now, think about how these functions actually apply to your real life on campus. Take an injective, or one-to-one function. It's exactly like the university assigning matriculation numbers. Every single student gets one unique matric number, right? No two students share the same one. When you understand the real-world equivalent like that, the abstract math suddenly just clicks right into place.
You also really need to watch out for the classic exam traps, particularly testing for even and odd functions. If you plug a negative x into the function and get the exact same original function back, it's even. Think cosine. But if you plug in a negative x and get the exact negative version of the original function, it's odd. Think sine. Honestly, when in doubt on the exam, just substitute that negative x and see what the algebra gives you.
Section 2. Limits and continuity decoded. We're shifting our focus here to where functions are heading and, well, where they completely break down. So when you evaluate a limit and get a scary 0/0 result, do not panic. That is literally just the math telling you to try another tool. You've got a tactical checklist. First, always try the direct method. If that fails, move right to factorization. If you have roots, try rationalization. And if you're dealing with really messy, complex fractions that still evaluate to 0/0, bring out the heavy artillery. L'Hopital's rule. Just differentiate the top, differentiate the bottom, and try again.
Knowing your shortcuts is absolutely crucial. And here is a high-yield formula you literally must commit to memory. The limit as x approaches 0 of sine of x over x is exactly 1. You are definitely going to see exam questions designed to look absolutely terrifying, but they're really just testing if you can factor out the variables to match this exact identity. Now, for a function to be continuous at a specific point, three things have to agree perfectly: the left-hand limit, the right-hand limit, and the actual value of the function at that point must all be exactly the same number. If they throw a piecewise function at you on the exam, where the rule actually changes depending on the value of x, checking the left side against the right side is your primary mission.
But what happens when those three things don't match? Well, the function breaks. If the left and right limits agree, but there's a literal hole where the function is undefined, that's a removable discontinuity. But say the left side approaches one number, and the right side approaches something completely different, like one heads to 5 and the other jumps straight to 10, you've got a jump discontinuity. And if it shoots wildly off to infinity, yep, you've found a vertical asymptote.
All right, Section 3. Conquering Differentiation Rules. Time to shift gears into heavy mechanics. This whole section is all about the rate of change.
When basic first principles fail and your equations start getting complex, you need an advanced arsenal of rules. Got a function stuck inside another function? Chain rule. X and y mixed together in a way you can't easily separate? Implicit differentiation. X and y both defined by a third variable like t or theta? That's parametric differentiation. The trick is to recognize the shape of the problem first and then apply the right tool for the job.
And remember, calculus works in the real, physical world through kinematics. If you have an equation for displacement, which is s, and you differentiate it with respect to time, you get velocity. Differentiate velocity with respect to time, you get acceleration. You are literally moving down the timeline of motion with every single derivative you take. Section 4. Integration and its applications. Which brings us perfectly to flipping the script and moving backward through the math.
Okay, the integration by parts formula might look like a total nightmare, but it is your absolute best weapon for integrating products of functions when basic substitution fails you. It basically takes a complex product and transforms it into a much simpler one. Memorize it, practice it, and trust it. It will absolutely save you on exam day.
And keep in mind, MTS 102 doesn't just want you to do the math, it wants you to actually apply it. You're going to be tested on finding the volume of a curve spun around an axis. You'll have to integrate acceleration to find velocity. Or, exactly like in tutorial sheet 7, you'll need to calculate the volume of water leaking out of a tank over time using an exponential decay function. Integration is really just the mathematics of accumulation.
Section 5. Strategic Thinking for Success. Finally, we are pulling directly from OEME's ORC sessions to build not just your exam mindset, but your broader life strategy.
The materials pose this really brilliant contrast: reactionary living versus strategic planning. Are you just reacting to poverty and chasing quick money, or are you actually setting a 10-year vision and acquiring the skills to get there? Because passing this exam requires the exact same strategic planning. Don't just react to the questions when they hit your desk. Anticipate them. Plan your study time intentionally.
I absolutely love this concept from the ORC notes. True innovation behaves exactly like a mathematical limit. It approaches its highest value through steady, purposeful refinement, not instant gratification. Whether you're solving a complex parametric equation or designing a solar backup for those campus power outages, you have to understand the root of the problem first. Guesswork fails in calculus, and honestly, it fails in real life too.
To manage exam pressure, and eventually your future career, you really need these leadership keys. Vision keeps you focused on the end goal. Emotional intelligence and self-awareness, they stop you from panicking when a question looks completely impossible. You just regulate your emotions, take a step back, look at your mathematical tools, and calmly execute the solution. So, FUTA 100 level students, you now have the blueprint. You know exactly how to tackle limits, differentiation, integration, and the mindset required to totally conquer this course. But I want to leave you with this final provocative thought. Calculus solves rates of change on paper, sure, but how will you use your strategic vision to change the real world? Master the math today so you can innovate for Nigeria's future tomorrow. Good luck on the exam, FUTA. You've totally got this.